In this set of videos, we'll discuss polymorphism. Polymorphism means many shapes. In C++, ad hoc polymorphism is when we can use inheritance and virtual functions along with dynamic binding in order to have our code behave differently for different types of objects. First, in this segment, we'll review type compatibility along with virtual functions, static binding, and dynamic binding. So first, let's get to type compatibility and inheritance. When a class is derived publicly from a base class, the derived class is considered type compatible with the base class. So let's look at this example. We have a person class and a student class, which inherits publicly from the person class. The person class is private data, only has a name and ID, but the student inherits that name and ID, and in addition has an integer for the major and a double for the GPA. Now, you'll see in main, we instantiate a person named Bill and a student named Joe, and then we want to see which of these assignments is possible. You'll notice that we can assign a student to a person, but we cannot do the assignment the other way. So this is right here. And the reason for this is that we can assign the derived class, which is the student, to the base class, but we cannot do the assignment the other way. And you can see how this makes sense. This diagram illustrates how this makes sense is because a person object only has the name and ID. So if we were to try to assign a person to a student, we would be missing information. In this case in particular, the major and the GPA. So a derived class can be assigned to the base class, but the base class cannot be assigned to the derived class. And so when we have a pointer or reference to a publicly derived class, we say that it is type compatible, which means that it can be assigned to pointers or references to the base class type. So in this example, we've added, in addition to the hierarchy that we had on the previous slide, where we had a person, a student inheriting publicly from person, we've added a faculty class which inherits publicly from person. So person is the parent class of faculty and student. Faculty and student are sibling classes. So we just want to see what the relationship is between parents and sibling classes that are derived. So inside main, we instantiate a person, Bill, a student, Joe, and a faculty member, Brian. You'll see that then we declare a reference to a person. And which is Q, we're calling Q, we can assign the person to the reference. But then you'll notice that we can also assign a student and a faculty to that reference. So here's what we're doing here. We can assign a person, we can assign a student, and we can assign faculty. And the reason for that is that they all have person is clearly type compatible with self, but faculty and student are derived publicly from person, so they are type compatible with person. Now I want to show you examples of what does not work. So now I have a reference to a student, R, and I set that equal to our student object. So that's fine. So a student object is type compatible with itself, but you'll notice that we cannot assign a person to a student reference. So this is, we cannot assign the parent or the base class to the derived class, and you cannot assign a sibling class. So they have the same parent, and you cannot assign sibling classes to each other. They are not type compatible. Okay. So now, let's look at static versus dynamic binding. So once again, using our person, student, and faculty classes that we had just defined, inside main, we instantiate a person named Bill, a student object named Joe, and a faculty object named Brian. And then here we have a pointer to a person object, Q. So initially we assign that pointer to the person object, Bill. And then we can call print info on that object using the arrow operator on the pointer. So Q arrow operator print info will call the print info function on the person object. And then we can assign the address of the student object for Joe to the person pointer because the derived class is type compatible with the base class. And then we can call the print info function on the student Joe's object. And finally, we can call the print info function on the faculty object. First, we assign the address of the faculty object Brian to the person pointer Q. That's fine because the derived class is type compatible with the base class. And then we just call the print info function. But you'll notice that what is printed out every time is just the name and the ID. So every time we call print info, even though we called print info on 3 different types of objects in the same inheritance hierarchy, we only called the print info function from person. So you can see that for each of these objects, for the person object Bill, for the student object Joe, and for the faculty object Brian, when we call print info, we are only calling the person's print info function to print out just the name and the ID. So this is called static binding. That means that at compile time, it's known what function is going to be called. And this is based on the type of pointer or the type of reference used. So in this example, we are always using a person pointer and calling print info on a person pointer. Because of that, we only call the person print info function. So that's static binding. At compile time, we know that Q is a person pointer to a person, and we would always just call the person's version of print info. And it's important to recognize that you'll notice that this is just a member function. There's no virtual keyword, which we'll get to in a second. And because of that, the static binding, it just compiler knows when this is compiled, okay, I see a person pointer, I always call person's version of print info. And it's just based on the type of reference being used. In this case, a person pointer. But now we want to think about, well, I don't always just want the person, just the name and ID. If it's a student, I also want the major and the GPA pointed and if, printed out. And also if it's faculty, I want to see if they're tenured or not. I want to call the specific print info function for each type of object. How do we do that? So the mechanism to do this is called creating virtual functions. So you'll see here that the virtual keyword can be placed before a member function. And when that's done, that tells the compiler that the function that should be called should be determined at runtime, and you should call the function based on the type of object being referenced. And this is called dynamic binding. So let's see what this looks like in this exact same example. You notice the only change we made was right here. We added the virtual keyword before the print info function. And now you'll notice that the behavior is different. So once again, we instantiate in main our Bill person object, our Joe student object, and our Brian faculty object. And then we have our person pointer. So that's the base class pointer. And once again, the derived classes are type compatible with the base classes when we use public inheritance. So when we call print info, when we have assigned this person pointer to person object, you can see that we are calling the person's print info function. However, you'll notice that once we reassign the person pointer to be the address of the student object and call print info, we will be calling the student's print info function. And you can see this because right here, we are printing out not just Joe's name and ID, we'll also print out the code for his major, and also the GPA is uninitialized. So here we're actually calling the student's print info function. And finally, once we initialize that pointer to be pointing to the faculty object, Brian's object, and we call print info, you'll notice that now we are calling faculty's print info function because we can say, okay, Brian is tenured. It prints out not only Brian's name and ID, it also prints out tenured to show that Brian is tenured. So this is an example of dynamic binding. It is a pointer to a person object, but based on the object that is being referenced, that will determine which version of the function is called. So when the object being referenced is the person Bill, we called the person's print info. When the object being referenced is the student Joe, we called the student's print info function. And when the object being referenced is the faculty member Brian, we called the faculty's print info function. Now, this is precisely polymorphism. So what we've done is we use a reference or a pointer to the base class, and we have them point to derived types. And then using the virtual functions, we can have different behaviors for each of the derived types. So this is an example of ad hoc polymorphism, where the virtual functions allow us to use one set of code that will operate differently on different derived types of objects. So now let's look at this exact same example, but now we're going to be using unique pointers. So you can see here in main, I declare an array of 3 unique pointers called people. Then I initiate each of those pointers to be objects that I create on the heap using make unique. So the first thing, just as in the previous example, I am going to make a person object named Bill on the heap, and I will store its unique pointer in the first position in our array of person unique pointers. Then I am going to create a student object, Joe, on the heap, and I will store the unique pointer to that student object on the heap in the second position in our unique pointer array or person unique pointer array. And finally, I will create a faculty object for Brian on the heap and store the unique pointer in the unique pointer array in the third position. But now you'll notice that we are only using one line of code here in order to print all of our objects. So we have just this one line for I equals 0, I less than 3. So for each of the person unique pointers we have in our people array, we need only call the print info function. So this is a pointer, just to refresh your memory, this people I is a unique pointer to a person. And since we have a pointer, we use the arrow operator and call the print info function. You'll notice that we get 3 different behaviors, and this is because the print info function is virtual in the base class, which is in the person class. So here, when we call print info for the first pointer in the array, it's a person object. So we call person print info. And for the second object, it's a student, so we call student print info. And then finally, for the third pointer, the third object is pointing to a faculty object, so we have faculty print info called. Okay. And that's one line of code exhibiting 3 different behaviors because of the 3 different objects that are being referenced. Now, just an important aside is that when you want to use dynamic binding and virtual functions in order to have polymorphism, the base class, you have to use a pointer or a reference or C++ reference variable and not copying a derived object. So let's look precisely what we mean by this. So you'll notice inside main, we instantiate a student Joe object, and then we call F1. F1 takes a pointer to the base class person. And because the person info function is virtual, person print info function is virtual, when we pass that pointer inside F1, it will call person, the person, it won't call persons, it will call the students print info. So you'll notice that the virtual binding works in an F1, and that's because we're passing a pointer to a person. Similarly, when we pass a reference to a person, so right here for the F2, we're passing a reference to the base class object. And when we call print info, the dynamic binding, we'll see, oh, this is a reference to a person object, but it's a student. So once again, F2 will call student print info. However, you'll notice that for F3, we're not passing a pointer or a C++ reference variable. We're actually passing a person object by value. That means we're copying the student Joe object into F3's person object. When we do that, there's no dynamic binding. This is an example. Static binding will happen. So you'll notice that the person print info is called. So the other 2 examples are dynamic binding, and this example, when you're passing by copy, you're just getting the static binding. Okay. Now, I wanted to discuss this example of what can happen if we were doing memory management manually and not using unique pointers. So here is an example where we actually have a class called a student, and then we have student with grades. And then rather than using a unique pointer for the grades, we are going to do the manual memory management. So what I mean by this is right here, this is going to be an array of integers on the heap. So dynamically allocated. Okay, so we have this dynamically allocated array of integers on the heap. So it will be our responsibility to allocate this array and also to delete this array. So right now you'll notice that in this example that we're looking on the left-hand side, we have a default student constructor. So inside main, we instantiate a student with grades object, and we save its pointer in the base class. The base class has just the default destructor, and you'll notice that the destructor doesn't do anything, doesn't know to delete any memory on the heap. So what happens is that because the destructor is not virtual, what happens is that when this item this object, student with grades object, is deleted, the student destructor gets called, the base class destructor gets called. And because the base class destructor is called, because it's a student pointer, so it's just looking, it's okay, I have a student pointer, I just call the student destructor, you would have a memory leak because there's nothing to get rid of that dynamically allocated array of integers on the heap. In contrast, you'll notice that here we change the destructor in the base class to be virtual. And what that means is that now dynamic binding is going to be used. So the virtual keyword indicates to use dynamic binding. So now we once again in main instantiate a student with grades object that dynamically allocates an array of integers on the heap to keep track of the grades. But now when we delete S, it's using the student, the base class pointer, but it's pointing to a student with grades object, the dynamic binding will look at, okay, what type of object is being referenced? It's a student with grades object. So here it will actually call the derived class destructor. And that's because the virtual keyword is there. It actually looks, it sees, okay, I have a student with grades object. It calls the virtual, because of the virtual keyword, it actually looks at the type of object being referenced. It will call the derived class's destructor. In this case, the derived class's destructor will delete the memory on the heap. So you will not have a problem with the memory left on the heap. So in the left-hand side version, when the destructor is not virtual, there's the potential for memory leaks. When you make sure that the destructor is virtual, you can make sure that it calls the derived classes destructors explicitly. So that's using the dynamic binding to make sure that the derived classes destructors are called. So that's a good practice, is if you need to write destructors, you should make the destructors virtual. If the default destructors aren't going to do the job for you. I want to mention an aside is that when we use unique pointers, for example, this is not necessary because the unique pointer, when it goes out of scope, will make sure it cleans up that memory for you. But if you are using more traditional manual dynamic memory management, then this is a concern, making sure that your destructors are virtual. Okay, just to summarize now, if you do not include the virtual declaration with the member function, static binding will be provided. And what we mean by that is that the function that's going to be called is going to be based on the type of pointer or reference. So that's known at compile time. In contrast, when a member function has the virtual keyword, that indicates dynamic binding should be used. And that means that the function called is going to be based on the type of object being referenced. So it's actually going to look at runtime as what object is being pointed to or referenced by this pointer or C++ reference and call the appropriate virtual implementation of the virtual function for that object. So that is how we combine the use of inheritance and virtual functions, specifically dynamic binding, in order to get polymorphism.